So here this diagram shows that how the rules will use for the port connections. You can see inside this box. You can see this inside the box. Normally, like we are having how many ports? Totally three number of ports are there. One is input, the output, another one more is in out actually. Now you can see here. Normally, this input will be referred as, normally it is a wire. Normally, the input will be referred as wire. This input. Normally, this input will be referred as wire. See, it's a wire, that is net. Then output will be referred as either register or sometimes net, in the sense can be a net wire also, or net I can say. Next, the in-out, that will be a net normally. Now, when you are connecting externally, you can see this is external, this and all you are externally you are connecting to that. Okay, when you are connecting externally, like if you want, you can connect to the input from the externally either with the register or net. In the sense, through externally you can connect with register or with wire also you can connect to the input. That is the rules. Yes. Next, for the output, you can say the output should be connect to the wire only. See, very important. Externally, the output should be connect to the net only. It cannot be connect to register. Next, you can see in out. It is a bidirectional. So I can say this will be connected. The externally is nothing but net. That is what the bidirectional. So here, which shows. See here, we are showing like this. See here, this input, this as I said earlier, the input that internally the input ports must always be the type of net. This is what as I said earlier. Externally, the inputs can be connected to the variable which is a register or a net. Output of same. Internally is output ports can be of a type register or net, but externally the output must be always connected to net only here normally. So they cannot be connected to register. This is what I said. If it is in out in the sense, then there is not an issue here. That should be connected to net. But here the one more thing, important thing is what? The width matching. Width matching in the sense, as I said, like the bit width, the output, the size of the output is 5 bit, means that is left hand side. The right hand side variable also must be the size should be equal. Width matching. So that is very, very important. It is legal to connect internal and external items of different sizes when making inter-module port connections. You have to be very careful while doing so. With mismatching will be there. Next, unconnected ports. What is the meaning of unconnected port? Sometimes the output port will be, sometimes it will be open. So at that point of else, it is like it is floating, I can say. It is unconnected. That is why the Verilog will allow a port to remain unconnected. For example, the certain output port might be simple for debugging purpose. So example, the output will keep it for debugging purpose. So in that, what you will do, sometimes you may not be interested in connecting to them in an external signal. Example, here we shown as full adder 4 FA0, the first adder. Some comma, you see here there is a gap. Some comma, there is a gap, comma A, B, C in. Here you can see the output port, the C out is not connected else. So how it will be in the sense, simple I can say, I will show with the diagram here how it will be. The unconnected port. See, this is your one full adder. This is the another full adder. Then this is you consider as FA1, full adder 1. This is considered as FA0. Okay, so this is A, this is B, this is Cn. Then this is sum. You see, this C out is not connected here, it's opened. So, but here it is connected. You can see example I'm saying. Okay, this is sum. See, it is connected. Now here it is not connected. Now what happened? This portion only I say see here. See now here it is not connected. This portion. So that only I can say it's nothing but here unconnected. So that is what here we mentioned is unconnected ports. So now sometimes the examples of some illegal port connection. Some example how it will be illegal. See module example top register. We are going to declare a connection variables register 3:0 a comma b. Keep it in your mind this. The register a b has 4 bit. Now register c underscore in it is a scalar value. Next the register sum is a 4 bit value. Then wire is a c out. Now we are going to instantiate. Instantiate the full adder, call it FA0. In the sense, full adder 4 add 4 is a component of full adder FA0 sum C out A comma B comma C in. Now you see very important, it's an illegal connection. Why? Because the output port sum, this sum, see the output port sum is a module F full add 4 is connected to the register variable sum actually in the module top. See here, I'll say here. See here, very important. See, the sum is a register actually, but I need to connect the outside in the sense, but this is the sum actually, output sum. You see, this sum. So that is what I'm saying in the sense because how so you may get the confusion here, right? So let me clarify clearly how it is in the sense. This is a test bench program. Keep it in your mind. This is a test bench program. So let me take this example, complete example for you. Let me take a complete example for you. Very easy for you. Yes, see. So now you consider this. Now this is the program of your test bench program. This is a test bench program. Okay, these are the registers. Okay. Top module, then stimulus here. Yes. So now this is the test bench program actually. Now you think this is a test bench program from where this will come. See this is a full adder. So this is nothing but a full adder, single full adder. Remember, this is a single full adder. How it will be single full adder? Normally, the single full adder will be like this. So here I will write like this. Full add 4. So here it will be like this in the sense sum comma carry out comma a comma b comma c in input. Then like the inputs are a b c. Then output is sum and c out. Then it's a full adder only, right? So it's a assign sum is equal to as you know a xr b xr c in. Then assign again statement. Then c out is equal to so some statements. This is under you know a b plus b c all the things. Then in module I'm not writing completely. In module. Now you see here, you can see the sum is declared as a output here. Okay, but how it is conducted here in the test bench here, we are instantiating the full adder, 4-bit adder. In the sense full adder, here the sum is nothing but what? The full add for sum is nothing but in the place of here, where here. This is we declare as a register, but here we declare as a output. So as we said, the port connection rule, what it says, from the main program, test main program, the output cannot be connected to externally to the register. So this is the illegal connection actually. So when you write this is what we meant. So this problem is rectified if the variable sum is declared as a net, that is wire, then automatically yes. That is the reason what we'll do normally in a test bench program. What we'll do normally in the test bench program. So the outputs are declared as wire, the inputs will be declared as a registers normally we'll do. Correct? So input will be stored. So this is what we'll do normally. So the connect port to external signals. We here some very important thing is that this is how we can connect the port to external signal. There are some two different methods are there to make the connection between signals specified in the module instantiation and the port in the module definition. Here two things are there. What are the two things? One is like you can connect by ordered list. As I mentioned earlier, we know that how we can do the mapping. Like say example component program. You remember that component program by order in the sense if you return the module output followed by input, then when you're doing mapping also that should be output followed by input. That position should be matched. That is what I said earlier. But what we can do here, we can do in one more way also. That is connecting the ports by name. That is namely wise instantiation. So there will be two different types of making the connection between the signal. That is one is by position wise, another one is namely wise. So let me show both actually how it has to be done. Connecting by the order list and the same way connecting by the namely wise. You see the example here. This is the example we are showing. Now first let me show connecting by ordered list. Ordered list in the sense you see. First you think this is nothing but your 4-bit full adder program. This side which I am showing in the right hand side. You see this? This is nothing but which one? This one. This is completely a 4-bit ripple carry adder program. So module, output, input, then some internals will be there here, then end module. Okay. Now you can see the corresponding test bench is written here. This is a corresponding test bench. So this is the corresponding test bench. So normally, as you know, the test bench program, the input should be declared as register, output should be wire. This is what the previous I said, illegal declaration. Can you remember this? Here it has declared as register sum. So here it is a sum. Sum is here output actually. The output cannot be connected to the register. That is why it is illegal. So only we changed it. So this is the corrected one. So here you can see in this, we called the full adder. Then this is the instance name. Now you can see the signals are connected to ports in by order. In the sense, see here which order we written here. It is output. Some see out both are output, then input. So in the same order only we written here. You see some C underscore out A B C. We not at all change it. This is what I can say. It is nothing but what? It is a connecting by ordered list. So here stimulus in the sense what your initialization values for A, B, all the values in right now, that only you can call as stimulus value. But now we'll see connecting by port name, how it will be like. Sometimes what will happen when you are having large designs. So at the time what will happen, so example you may have around 50 ports example. So you cannot able to remember the order of the ports. If it is 4 ports, it is very easy. Say example A, B, C, some C out means it is easy for me to remember. But if you are having around 50 ports, so it is very difficult for us to remember. At that time at that time we can use the connecting by port name. So it will be very easy. Instead of using the position, just we can map it name with the name actually. How it has to be done? So that we can see here. The example is like this. See how we have to done in the sense same this program same only. Okay, your 4-bit adder. This program is same. This won't change. I am going to show only this portion. Okay, you remember this is output, output, input, input, input actually. Now here I will change it here. Instead of going the same order, I want to change the order. So how it has to be written in the sense, see here, see like that, see. So full adder, FA by name, see dot C out of C out. You see which is which one? We need to know, correct? This is lowercase, this is uppercase. Now, how we will map it in the sense you think of lowercase and this is which one? So this is the lowercase. See, this C out is mapped with this C out, but that is written in the first place. I hope you got it now. That is written in the first. Next, this A is mapped with this A. Then this B is mapped with this B. Then this C in is mapped with this C in the sense it is connected. That is the meaning of that. Right? So now what I did, that is what we did here. See how we have to write? See, dot. You have to write like this only. Dot C out. This is connected to C out. Within the bracket you have to write comma. Dot sum within the bracket to which sum it is connected, then dot b to which b it is connected. So you have to write like this. Then if you write in the sense, so it is the order also change. You see, C out, sum, b, c, a. See, we change it. Even though if you give like this, but properly the corresponding port, the variables are mapped, properly it's connected. So it won't give you any error. So we can use like this also. Sometimes the port C underscore out may not connected. Example, sometimes it may not connected. So what you will do at that time? So at that time you have to do like this. See, full adder, then that instance name dot sum of some comma. Then where is your? See, we missed out. It's not there. Even you can leave out here. If you leave also no problem. Dot p of p comma c in then a. So it won't give you any. See, comma is there. After that, there is no. See, after this, see, we ended with the comma here. After that means that is a open port. That is meaning is one variable is not connected. That is the meaning that if I'm not given this comma over here, then automatically it will give you error. Why? Because the full adder has 2 output, 3 input. Totally 5 actually. So 1, 2, 3, 4 only will be there. So it won't match it properly, automatically it will give you the error. You should use a comma. If you use a comma, the system will understand by default the last one more port is not connected. It is unconnected. It's kept as unconnected. That is the meaning of that. So normally that will be dropped from the port list. So if you use this, what is the advantage of this? If you use, so continue port by can be rearranged without changing the port connection in module. So here I showed two same name only be shown. Even let me give a simple example how it has to written also here. One is position wise, as you know, position wise instantiation. Position wise instantiation. Okay. Now what I'm doing, full adder using 2 operator. Example, let me take full adder using 2 operator. So full adder using 2 operator in the sense module full adder A comma B comma C comma S comma C out. Then as we know, input is, I'm not going to write the complete program. A B C, then output S C out. Then what will happen? We'll have the connections here. See, all the things will come here. Then end the module. Now what I need here, example I'll say here half order. Okay, example I'm saying HA1 half order, right? Anything I'll do half order in the sense I'll take A comma B, first half order A comma B, maybe the wire will be there. So just I'm writing wire S1 comma C1 comma C2 normally. Half a full order using two half orders. So wire will be there. So A comma B comma S1 will be there. Half order. One more S1 comma C1. So like again second half order will be there. Next one OR gate will come. Then N module. For position wise half order. Now what I need to write the half order program here. So module half order. What I'm going to write instead of ABC, I'm going to write as X comma Y A comma B comma S comma C. Input AB, output SC. Then you know that what is the statement should come. Then finally N module. Here our statements will come. Now you can see the positions will be very simple. We can think here A comma B comma S1 C1, then A comma B SC. It is both are all in same position. A is input, B is input. Same here, A is input, B is input. So input, then SC is output, SC is output. See S1 and C1. It is a wire. See normally, as I said, you know that in this, when invoking, the output can be connected to wire, not a register. Correct? It should be connected to wire only. So it is connected to wire actually. So now, as I said, this is position wise. This position wise. Now, namely wise. Here only I'll show. Namely wise. Instantiation. Namely wise instantiation. Now, what I will do for namely wise instantiation, same I take, same program only. See now, I will change this as something like a X, Y, XY, I'll change to XY this. Both are input. Okay. Now, what I will do here, instead of that, which I am doing here, simple, I will do how it has to be done now, from where to where you are doing. So, like HA dot the full adder dot HM calling, right? Here, this A only, okay? This A actually. A, it is connected to here only. It is connected to X. Then that B is connected to Y. Dot B you have to specify. Then comma dot, where is C? That is there any C? No, actually, because using operator plural. Next, yes. This S is connected to S only, because here also is specified S only. Next, the C out, the output, right? The full adder C out. No, actually it will come wire. Which one? S1 wire. S1 wire is connected to where? C. See? Because as you know, the first half adder input will be like this. Okay? See? This is half adder, first half adder. This is the first half adder A, B. That is something but this one. S1, C1 it will go. Right? So that is what we given. See here. So that is what I said. I change, we can change it this also. See, even you can write like this also. Even instead of that, I can write like this also, alternate way. See, this is I change the positions. Now what I will do, J1, just let me write like this. Dot S of S, dot B of Y, dot, this is A, right? Yeah. Dot S1 of C, then dot A of X. See, I changed the order only. You can see this. Order changed here. Even though if right, it will work. But what I did the mapping with the namely wise instantiation. See, the name wise instantiation we done. But here we done position wise instantiation. See, but here I did both actually. It is position wise as well as name wise also. Namely wise I did, but it is followed the position actually. So this is the alternate way you can write. Now hierarchical name. Sometimes we described earlier how the Verilog will support the hierarchical design methodology. Like every module instance, signals or variables is defined with an identifier. So here, how it will be in the hierarchy in the sense we shown here. See this? We have to do like this. Like normally, if I say SR latch, how the hierarchy will be there in the sense we can say in this, the stimulus is the root level normally. From the stimulus actually the hierarchy like it will take us M1 SR latch. What is this M1? You can go back to your SR latch program actually. So in this what will be from the stimulus root level it will go for M1. It's an instance name with this SR latch. Then Q bar, set, reset. These are the variables. Then again from the SR latch here it will go to NAND, that is N1, first NAND gate, this is the second NAND gate, then Q bar, S are signals. Normally, how it will be done in the sense is simple, I can say. This hierarchical name is a list of identifier separated by dots. This hierarchical name is a list of identifiers. These are identifiers we use here, the identifier. These are all the identifiers which we used. So it will be in terms of dot for each level of hierarchy. So the any identifier can be addressed actually from any place in the design by simply specifying the complete hierarchical name of the identifier. How it has to be done in the sense, let's see example. If you want to access in the SR latch any point, so like how you can access in the sense, you can access in this way. See here, example, stimulus was there. I need to access the value as like a Q bar value. So how can I access in the sense? First stimulus, the hierarchy will be like this. First stimulus was there. Next stimulus star Q bar dot. See here, stimulus is a root level actually. That will go to M1. This is like your test bench program oriented. So you see, remember in your test bench how test written your test bench program like module, then register wire will be there. After that you have to instantiate. When you are going to the instantiation, like what will happen in that first label it. This is SR latch. The component will go. Inside the component, we'll have this identifiers QQBar set to reset. Then again, internally, if we see what will happen, this will communicate to the main program actually because you are going to test the SR latch. This SR latch is made up of two NAND gates. So then the hierarchy variable will be QQBar S and R actually. So that is why see from this first stimulus, it's a root level normally. So stimulus dot, you have to do like this dot Q bar. See which Q bar? This Q bar first. As per a diagram from the next step. Stimulus dot reset. Sorry, it will come like this. It is order is like this. Stimulus next to stimulus is stimulus dot Q. Next stimulus dot Q bar. Next stimulus dot set. Next stimulus dot reset. See it has go like this. Hierarchical will go in this way. See like this. Stimulus dot Q, stimulus dot Q bar, stimulus dot set, stimulus dot reset. Next stimulus dot M1. See this stimulus dot M1 dot Q because this M1 is connected to this Q. This is hierarchy. You can see this Q is connected to M1. This M1 is will be under the stimulus. I hope you understood that how it is coming the hierarchy. See here, same like this. You see this stimulus M1 dot Q bar. Next stimulus dot M1 dot S. You have to see the diagram actually. Next is stimulus dot M1 dot R. Next stimulus dot N1, stimulus dot N2. Because this is nothing but stimulus dot N1 is nothing but your NAND gate symbol. This is not the variable actually, correct? This is internally we given NAND gate 1, NAND gate 2. So if you want to access any point, anything, if you want to access root, so easily you can access the value for this stimulation. The stimulus is a top level module. Since the top level module is not instantiated anywhere, so it is called the root module. So now the identifiers define the modules are Q, Q bar, set, reset. The root module instance M1, which is module type of SR latch normally. So this is the explanation is given for that actually. As I mentioned here, you need to know about this diagram. Show the diagram. I think it will be easy for you. How it is done in the sense, like as an example. See, I hope it is NAND gate based. See, this is S bar, this is R bar. Sorry, this is R bar, this is S bar, then Q bar. So this is what actually they written by hierarchical wise. This is N2. Here it is written for this one especially. For this diagram, it is written stimulus root level like M1 SR latch. This SR latch complete the module name is M1 is specified module name. That is the thing is written here. M1.s all that. So it is like this order will go in this way. Order will be like this. First it will go in this way. Next it will go like this. Then it will go in this way. Then it will go like this. See, this is the order actually. Stimulus order. Now in this, each identifier in this design is uniquely specified by the hierarchical path. This is the path. Stimulus, then M1, then R. Stimulus, M1, then QBar. So easily you can access during the simulation. This is actually during the simulation only we have to access if you want to access. So use a special character $M. See, not dollar, sorry, percentage M in the $display task function to display the level of this hierarchy. If you want to display this level of hierarchy, what you have to do in the sense, you should use the system task function, that is $display task. In that you have to use that is percentage M. If you use, we'll get like this, we get the system. This is what. So these are the some exercises are there. You can go through all these exercise. So very little bits are there. I hope I might have sent some materials in the Google Classroom. You can go through those things. So if you are having any more doubts, you can ask.